There's the 30 students in math class. And at least B contains the 35 students in an English class. And suppose there are 20 names on board list. Find the number of students A only on list A, B only on list B, C on list A or B or both, and D on exactly one list. So this is the text question. Sometimes, text question is look like harder than, diagram question. But we can solve easily. If you want, we can draw a diagram or okay, let's do diagram to explain the question. It's gonna be easy as a solution. So we have again universal set and set A. They are not disjoint. There is a set A and there is a set B. There is the intersection sign for A and B. Okay, what is the question is saying? A contains 230 students as a math class, is the A, and B contains 35 students. And for both, we have 20 students is here, right? 20. So it means there's this 10 student more here because totally as a 30 and B contains 35. It means there's the 15 more student. Okay, I will make some place here to write solution and case A. So what is the answer for case A? 10, right? Only on list A is 10. And how about B? Is it 15? Exactly. I'm really happy. So your answer. And C, and for both, mm, this is that theorem. Okay, number of A union B as a total, 20, 30, and 45. And B, yeah, actually this is equal number of A as a or, or means as an addition number of B. So there is some common element, and you apply to formula like that one. But here is the three cells, we have two cells, and then you will make 30 plus 35 minus 20 is gonna be is equal 45, and B is a little bit uh, different. Actually, it is the questioning as a symmetric difference A and B. So this is equal 25. Symmetric difference means only A and only B, and 10 plus 15, it is the 25. Yes, exactly. In one list, there will be 10 plus 15 as a 25 student. Okay, let's continue. As a new title, page 5, classes of sets. We will talk about the class and power sets, and partitions. Okay, let's say there is as a set S, like the given as set S, we might wish to talk about some, it is subset. We will talk about the subset. Thus, we would be considering a set of sets whenever situation occurs such a situation occurs. To avoid confusion, we will say a class of sets or collection of sets rather than a set of sets. So we will say as a class, if we wish to consider some of the sets in a given classes of sets, then we speak of subclasses or subcollection. Example, let's say we have an example, let's say we have S, and inside of the S there is the element like 1, 2, 3, and 4. Okay, A for that situation. Let's say there's the a class of subsets of S which contain exactly three elements of S. So we can write the this class of A like that. There is the 1, 2, 3, and 1, 2, 4, and 1, 3, 4, 2, I'm sorry, we will define parentheses here, 2, 3, and 4. In brackets, I show the class A. Class A has subsets of S as a 3 elements. And B, let's look at the case B. There is a set B class of subsets of S. There is this something is not correct. Okay, let's say something is different. B, a class of subset of S, and which is also subset of subset of A. So we can write for the B, B is the class of subset of S and also subset of A. Okay, I can write here as a 1, 2, and 3. and 1, 2, and 4, and 2, 3, and 4. So for the classes, I'm using, brackets instead of the, different parentheses. And, B and R also subset class of the S set. And let's find the new definition as a power sets. We talked about the, class of sets, and now power sets. And if we are looking for power sets for a given set S, it means we speak about of the class of all subsets of S. So we are talking about the all subset of S. It means we are talking about the power sets. So we can say, of course, this class is power set of S. So we can denote or represent of the number of power set of S as is equal to the power number of S. The example, okay, let's say we have S is equal 1, 2, and 3, 1, 2, and 3. So find the power set of S. What is the solution? It is easy, right? And where is writing? Yes. It is the 3 as a solution or answer. And number of power set of S is equal to the power number S. Number S is 3 as a 2 to the power 3. This is equal to 8. Okay, now power sets is really easy. Okay, if you want to write the power set of S in our new page. Now we are on page 6. Okay, power set class of the S is equal, in brackets there is the empty set and 1, and set 1, there is the only set in that set as a 1 element. And here is the 2 and 3 and 1 and 2, 1 and 3, 2 and 3. There is also set S. Any question? A partition. Yes, of course, I'm going to upload that lecture note to UBIS. The partitions let S be a non-empty set. A partition of S is a subdivision of S into non-overlapping non-empty subsets, precisely a partition of partition of S is a collection in set AI of non-empty subsets of S such that we can say as a first each A in S belongs to one of the AI. And second, the sets of AI are mutually disjoint that is if AJ is not is equal AK, then AJ intersection AK is equal empty set. Okay, there is the and okay, let's write something as a definition. The subsets in partition are called self and Venn diagram of partition of the rectangular set S of points into 5 cells like A1, A2, A3, A4, and A5. Example, S is equal 1, 2 is equal to list of elements 1, 2, 3, 4, 5, 6, 7, 8, and 9. We have the sets like that. Let's write some classes of that set. Previous something. We have to represent here or show the diagram of S as a 5 cells like that. A1, A4, 5, B into A1, A2, A3, A4, and A5. Okay, let's look at that example back again. There is the case 1 in subsets as a 1, 3, 5, and 2, and 6, and 4, 8, and 9. We have 3 set as a subset class of S. And second one, we have again class here which belong to some subset of the S as a 1, 3, and 5. And there is a 2, 4, 6, and 8, and 5, 7, and 9. And that's all. And third one, again we have some subset class here. The 1, 3, and 5, 2, 4, 6, and 8, 7, and 9. That's all. And we saw some partition of S using some subsets and subset classes like that. There is the some notation to generalize the set operations. We saw some details. Okay, let's write that one also in new page. Or okay, let's start here. The set operation of union and intersection. The set operations of union and intersection were defined above for two sets. These operations can be extended to any number of sets finite or infinite as follows. So what are those? In page 7, consider first a finite number of sets, say A1, A2, and so on, AN. The union and intersection of these sets are denoted and defined respectively by like that, A1 union A2 union and so on union AM is equal union I is starting 1 to M, which is AI. This is a generalizing way. X, which is member of AI for some AI. If there's intersection, A1 intersection A2 intersection and intersection AM, again union, intersection starting with the I is equal 1, I is equal 1 to M. Again, AI is equal, there is the X, which is X, the member of AI force for every AI. So this is the notation as a generalized set operation. And I think there is the example But before the example, um, different notation again, that is the union consists, as I remember that notation used in some examples, that's why I'm writing here. At least one of the sets and the intersection consists of those elements which belong to all sets. Now let A, the fancy A, be any collection of sets, the union and the intersection of the sets in the collection. A is denoted and defined denoted and defined respectively by union A. A is member of collection A, which is equal X, which X is belong to A I, or some AI is a member of collection of set A, an intersection A, which is the member of collection of A, and there is as a X, which X the member of AI for every AI, which is a member of collection of A. So there is the example, and but I will jump that example. Example 1.12. Please check that example. And there is as a new title, mathematical induction. So Osama say something, it cuts off. You mean the video screen or screen? Sometimes 10 minutes ago, now it's good. Yeah, sometimes we have a problem like that. The mathematical induction Let's start that one, and I will finish this lecture after to write some part of that title. Next week or next lecture, I hope we will start chapter 2. Maybe we can solve some example, but in that chapter, examples also really easy. You can check the examples. There is a solution also. You know, that book is really good to get the idea when you study by yourself. Okay, let's try mathematical induction. Okay, you're writing something. Okay, I will try to upload today's note. I mean, 1, 2, 3. Is that okay? To somewhere of positive integers follows principle of mathematical induction. Induction I making place. Let P be a proposition defined on positive integers and that is E n is either true or false for each an element of the set n. Suppose he has following he has the following properties. One, P1 is true, one is true. And second one, P k plus 1 is true whenever pk is true. And let's complete here. Then I will finish the lecture. I mean today's lecture. Then P is true for every positive integer n is element of set n. We shall not prove this principle. I mean, your book is not giving any proof. In fact, this principle is usually given as one of the axioms when n set n is dual axiomatically. Okay, there is an example. Next lecture, we will continue with that example, and then we will complete, we will complete chapter 1, it's the page 8. Today, I will try to share that note with you. We have totally 8 pages. And any question? Okay, thank you, dear friend, coming to my lecture. I'm happy to see you and your response. Even you are writing as a simple something. And next lecture we will continue. Then we will start probably to chapter 2. Okay, see you next lecture. Have a good day for all. Healthy and happy days in that harmony creation.